G'day, it's Richard Marr again from Mars Classes. Today we're going to be looking at gravitational field strength. We're going to define what it means and have a look at the units which are used to describe it. Before we'll have a look at Newton's laws. Now, Newton's first law says that an object in motion will continue in that state of motion until a force acts on it, and when the force acts on it, it will change the motion. So let's just imagine the moon was travelling in a straight line. It would continue to do that until some force acts on it. It doesn't travel in a straight line, it actually orbits the Earth. So the Earth must be applying some sort of force to it. Now we call this force a gravitational force. And we can represent force because it's a vector by vector arrows. So in this instance, when we look at the Earth, all the vector arrows are pointing toward the centre of the Earth. Now that vector arrow represents the force that's experienced by that moon which is orbiting it. But it's also the force that any object would experience if it was sitting on the surface of the Earth, or sitting at some height above the Earth, or even further away from the Earth. It would still experience a force due to the gravity, and it's actually a force due to the curvature of space. So what we're going to do is we're going to have a look at these three locations that I've labelled here with those orange circles around the Earth. Now on the surface of the Earth, we look at the vector arrows. They're all pointing toward the centre of the Earth, and they've got a certain density. A bit higher up the density is less, but the direction is the same, and further out the density is even less, but the direction is still the same. So let's now place an object into this gravitational field. We'll place an elephant at a certain elevation. Now, we're saying that it should move along that vector toward the Earth due to the Earth's gravitational field. But let's say we placed an elephant of the same mass, identical mass, at an identical height. Would those two elephants experience the same force? I think most people would say yes, that's probably true. Let's say we placed another animal, a little mouse this time, at the same elevation. Now, the mouse has less mass. Would it experience the same force as the elephant? Well, that's a question we've got to consider. And if we put another mouse at the same elevation down at the lowest part of the Earth, we ask the same question. Those four organisms there, are they all going to experience the same force? Are they all going to accelerate toward the Earth at the same rate? Let's simplify the diagram. They're all going to follow along those vector arrows. They'll all fall to the Earth. Will they fall at the same rate? Now, this is a question that people have pondered for a long time. Does an elephant fall faster than a mouse? Does a bowling ball fall faster than a tennis ball? Do heavier objects fall faster than lighter objects? So let's do some thought experiments here. Let's lift that elephant back up to its original elevation. Now we know it's going to fall with a certain rate. Let's now change the situation and stick the mouse between his toes. Now if we do that, if we were making the assumption that the mouse falls slower than the elephant because it has less mass, now we've got the situation, does the mouse elephant object fall faster because it's got a total mass larger than the original mass of the elephant? Or does it fall slower because the smaller mass of the mouse, which is falling slower we're assuming, slows down the elephant above it? Or does it fall at the same rate? To answer this, we're going to have to look at some mathematics. We know that the force that these objects experience is proportional to the size of their mass and the mass of the object they're being attracted to and the distance between the two objects. And to go from proportionality to actual measurement, we can multiply by the universal gravitational constant and we get the size of the force in newtons. So let's just compare the two forces these objects experience. Let's compare the force of the elephant to the force of the mouse. So the expression down below gives us an expression of the force. So let's have a look. That ratio on the left, the value on the left is proportional to the value on the right. But we can cancel out parts of that expression which are identical. The universal gravitational constant is the same on both sides, so that can be cancelled out. The mass of the Earth can also be cancelled out, as can the distance between the two objects. So we end up finding that the ratio of the force that the elephant experiences compared to the force that the mouse experiences is identical to the ratio of the mass of the elephant to the mass of the mouse. Now that's interesting because a lot of people would say, well, that goes to prove that the elephant falls faster than the mouse. But I'm going to go on now to prove that all objects independent of mass will fall at the same rate. We know that the force that the elephant experiences is proportional to its mass, as is the force the mouse experiences proportional to its mass. And we also know that the force that they experience is equivalent to mg. Now, a lot of students will say that, read in words, they'll say the force equals the mass times gravity. Just beware, when we say gravity, actually the G represents something to do with gravity. It's not gravity itself. So later on we'll explain what G actually does stand for. So when we look at that, what is G? I mean, what is it? If we manipulate the equations, we see that it is force divided by mass. So if we've got that, and we know that the force that the elephant experiences compared to the force the mouse experiences is equivalent to the mass of the elephant ratio to the mass of the mouse. What we find out there is the force of the elephant on the mass of the elephant will be equivalent to the force of the mouse on the mass of the mouse, which means the value of G for both of them is identical. So what that says is that for both objects, no matter what the mass, G will be the same. Now that's really important. So it doesn't matter if we've got a semi-trailer and a motorbike, or a bowling ball and a tennis ball. The G for all objects at the same height in the Earth's gravitational field will be the same. So let's have a look at the units of G, and that'll give us an idea what G actually represents. If it is force divided by mass, the unit's going to be newtons divided by kilograms, or newtons per kilogram. And we know that newtons are defined as, 1 newton is defined as 1 kilogram metre second to the negative 2. So let's substitute for the newton in the original unit, and we'll find that the units of G are therefore metres per second per second. Now what do we know metres per second measure? They measure acceleration. So the symbol G actually represents the acceleration due to gravity, or because we've got newtons per kilogram, it's also described as the gravitational field strength. So when we say F equals mg, don't say it's mass times gravity. Say it's mass times acceleration due to gravity, or it's mass times gravitational field strength. That's a far better way of expressing that in words. So we know that the weight force is mg. On the surface of the Earth, the value of G is 9.8 meters per second, or 9.8 newtons per kilogram. It doesn't matter what mass it is, all objects will accelerate toward the Earth at the same rate. Okay, we'll do more on this later on, but until then, I'll see you next time.